I'm Mark Ritter, Principal Engineer at Postman. Today I'll be talking about how latency can show up in surprising places, how our abstractions of system behavior can obscure what's actually going on. I've picked some examples from my past career that illustrate the need to expand our view of to the entire stack of causes when debugging latency issues. I'll hope you can come away with this with some ideas of where else you might need to start looking when your service is ill-behaved. I've been working on monitoring and observability solutions for APIs at Akita Software. We were recently acquired by Postman. Previously, I built VM-aware flash storage arrays at Tintri. So today I'll be talking about surprising sources of latency. So where does latency come from? What causes it? I'm a developer, and my first instinct is to always look at things I can directly control, my code. Latency is from function enter to function end, right? So if I'm seeing long latency, it must be because I made a slow database call, or I waited for a lock, or I missed in a cache. Maybe I allocated too much memory and triggered a garbage collection cycle, or I used an inefficient algorithm, or did something else that I can easily measure and control. But the things I can directly control in my backend service are just part of the picture. There's usually a network in the way. We can picture it as this nice interaction diagram with convenient client and server boxes and ask things like, well, am I sending too many messages back and forth? And, these can be real problems. But this is still a lie. Our client is not a single entity either. It runs on an operating system and often inside some sort of hypervisor. So does our server application. An API call isn't just one round trip. It could be lots of them as TCP establishes a connection and TLS secures it. In between, there could be load balancers, firewalls, other sorts of middlewares like a service mesh that can delay or reroute our traffic. Our client might make calls to completely unrelated services like DNS. And all these other things are just software recursively running on operating systems or hypervisors of their own. So this means there are queues and delays hiding nearly everywhere. So when we think about the long tail of system behavior, any of these factors could come into play. We have to understand the whole stack of factors and infrastructure that influence our application's end-to-end behavior. So let's look at some examples I've encountered about how these abstractions conceal unexpected sources of latency. One of my first jobs was a startup that was building streaming video hardware. The hardware needed video to be prepacketized in units of a megabyte, and I was building the software to do this pre-processing. We wanted to be able to handle live TV with a small delay, as well as preloaded content like movies. A standard definition stream, still common back in the ancient date of 2001, was about 3 megabits per second. And so a megabyte block was about 2.7 seconds of video, which we delivered over TCP to a storage device, which then loaded it into a streaming engine. So the schedule wasn't highly demanding. 2.7 seconds is quite a lot of time. But once in a while, we were several seconds late delivering video to storage. So we tried to track down the problem and looked for all the usual suspects. Was there lock contention? Was the algorithm I was building occasionally inefficient? Was my process not being scheduled correctly or hanging on memory allocation? My manager at the time even helped me write a custom tracing tool so we could see what each thread was doing. My coworkers and I at the time were networking nerds, so of course we looked at TCP dump traces to see if there was a delay in transmission. From the receiving side, the transmission seemed fine. It was just starting too late to even hit our deadline. But we finally made the same set of observations from the sending side and realized that this picture was closer to correct. The block was ready on time. We opened up a new TCP connection to send it, and the initial SYN handshake message just got lost. Normally, a missed packet would be quickly resent, but the initial SYN packet is retried only 5 seconds later, which is an eternity compared to normal recovery on a point-to-point link. So we could have looked at improving our TCP connection pooling and found a way to always use a warm, already established connection. But we were compiling our own kernel anyway, so our solution was to reduce the initial retry to a few hundred milliseconds, which absolutely solved the problem. So of course, I learned a valuable lesson here. When your system experiences high latency, blame the creators of the internet. My next job was storage, and anybody who has worked in storage can tell you that storage is always to blame when an application is slow. At Tintri, we built a flash storage array specialized for virtualized workloads. A potential customer using VMware was seeing high I/O latency and had decided it was time to upgrade their storage from disk to flash. They rolled in a competitor's very fancy all-flash storage array, and to everybody's surprise, nothing improved. Storage was still slow. And this gave us a shot at the problem, so we put our array in their infrastructure. Most of the time, a virtual machine feels like real hardware. So the virtual machine sends a request to storage, it goes over the network, the controller looks at it, dispatches it to flash storage, and sends the response back. So latency is the combination of network latency, controller overhead, and device speed, correct? But this is the wrong picture to explain what's actually going on. A more accurate picture of the world acknowledges that the I/O response is first received by the hypervisor. The virtual machine is scheduled to run if it's not already, but the hypervisor might not get around to it right away. The component missing in our latency equation is the time the virtual machine spends not running. So why could this be? Why might the hypervisor introduce extra delay above and beyond the simple overhead of context switching or translation? And for many of our customers, it turned out to be swapping. Pages in the virtual machine had to be fetched back from storage before it could handle a response from that exact same storage. In this case, the explanation was a little more subtle. In VMware, all the virtual machine CPUs have to be scheduled together. If your VM says it needs 8 vCPUs and you only have 7 CPUs available, that VM is going to have to wait. So the scheduled machine could be sitting 7/8 idle until that physical CPU frees up, allowing us to finally schedule the heavyweight VM. And you typically give your big I/O-intensive database server lots of CPU, right? At Tintri, we tried to show this larger picture to the storage administrator. We could measure latency locally, in our case, not for each virtual machine, not just the entire array. We estimated the network latency using packet inter-arrival times, and we asked the hypervisor for its measurement of storage latency. From this, we could estimate a calculation of how long the virtualization host was contributing to latency and show that measurement to the user explicitly. We back this up by showing the hypervisor stats most associated with the problem host cases, swapping and scheduling delays. And this saved some of our users literally weeks of finger-pointing meetings and showed when the latency wasn't the storage's fault. So I also learned a valuable lesson here. High latency is caused by having too much CPU. Another example from my time at Tintri shows how the network is sometimes not a straightforward point-to-point connection. Tintri's storage arrays uploaded auto support report periodically containing diagnostic information. We noticed a problem though. The backend auto support system thought the upload succeeded and put it in S3 for later use. The storage array disagreed and thought the upload had failed. So the array would try the upload later, leading to a lot of identical duplicate reports. And so I was called in to look at this system somebody else had built and what's going on. Our upload was not a particularly sophisticated protocol. We built some of those later, but this was just an HTTP post with an end-to-end checksum and a header. How could the client and server disagree so badly, and it turned out so consistently, about whether the upload had succeeded? We knew the data was not corrupt or truncated because we looked at the checksum. Logging and debugging in our software showed nothing particularly unusual, just a kind of weirdo TLS error, which we eventually figured out was an obscure way of telling us that the connection had closed unexpectedly. And of course, I used TCP dump again, and because I had learned my lesson, I captured traces on both sides of the connection. And what I learned from that is while the server saw a bunch of bytes arrive and then a connection closed with FIN, like it should be, the storage array saw a bunch of bytes go out, followed by a reset from the server. So the two sides did not even agree on whether the connection was successfully terminated or not. But unfortunately, that picture was a lie, because once I matched up the timestamps, I saw that the server thought the connection was continuing for far longer than the storage array sending that had established the connection did. And so the picture I put together was this. The array was sending data very quickly to an elastic load balancer, but ELB was sending the data very slowly to the server. Eventually, the server ran out of things to send. The load balancer waited a while and closed the connection because it's idle, but it kept streaming data into the server anyway, and the HTTP 200 response from the server was just dropped on the floor. Effectively, the load balancer was creating negative latency because the client saw an error response before the server even finished. At the time, we didn't really need two upload servers, so we actually removed the load balancer, but I also, in this case, finally fixed the underlying problem, which turned out to be fairly silly. The code as originally written was reading from the network 1 byte at a time. It sort of makes sense to me today that ELB doesn't do a pure cut through, but at the time I was very surprised that it had tens or even hundreds of megabytes of buffering, and I still don't know what the upper limit is today. I also wish that they terminated the server connection when they tore down the client connection. That would have made the failure a lot more obvious. In any case, the valuable lesson I learned here is AWS services cause or maybe subtract latency. This is a catchphrase. It's a catchphrase for a reason. Yeah. Before I was a startup nerd, I was an academic, and we've known DNS is a problem, at least to academics, since the early 2000s. There was a ton of research about how to fix this, distributed hash tables, other stuff. As far as I can tell, none of it got applied, and we just got operationally better at running DNS, including, in some cases, running DNS over HTTPS. However, I still think this fundamental result holds that DNS is not normally slow, but when an HTTP request is slow, it's disproportionately likely to be time spent waiting for DNS, particularly if there's still a 1 second or worse, a 5 second retry time baked into the resolver. So what are we going to do about all this? The real lesson I take away from my examples is not that TCP is bad or hypervisors are bad or that AWS load balancers are bad. It's that latency is hardest to deal with when it shows up in some place you ordinarily ignore. And unfortunately, network systems are complex artifacts, and you really do have to make assumptions to get through your day. But bad behavior can crop up anywhere, from the client software to the client's software and physical hardware stack, to things in the middle, to your server stack, to your application's dependencies, to client dependencies like DNS. The easiest place to start is by expanding the scope of your measurement to cover more of the system. If you can measure the same transaction on both the client side and the server side, then simply putting those measurements together in the right way starts giving insight, rather than just assuming that you know how they fit together. Look for differences between failure and error rates as reported by your server and your client. Look for differences in duration and latency. In my example of auto support uploads, a negative latency should have been a huge red flag. We can also expand the scope of what we put in our measurement or span. Instead of measuring a function latency, can we measure the entire server's latency? For example, maybe we could get an eBPF probe to tell us when the request actually arrived, not just when the operating system or our application framework finally delivered it to our code. Could we look at the network and build a better picture of the entire sequence of events that led to the bad behavior? And when there's a mystery, we can start drawing our whole picture. The network is not just a network, it's a buffer. The client is not just a piece of software, but a whole application stack of its own. The server is not an isolated system, but its performance depends on numerous factors, not, unfortunately, all directly under our control. At Akita Software, and then the work we're doing for Postman, we use packet capture to try to get a better picture of the ground truth about how API calls appear and are handled. At the network layer, you can both estimate server time from the last packet of the request to the first packet of the response, but also get a bound on the total end-to-end latency based on the observed times of the first and last packet of the whole sequence. If you're really ambitious, you can estimate round trip times too, or find places where packet drop is causing retransmission. There's just a lot of data here that isn't in an application level trace. If we're interested in tail latencies in the P99s and P999s, by definition, we're looking at something unusual, something that rarely happens. So we might have to look for it someplace we wouldn't ordinarily think to look. Thanks a lot for attending my talk. You can reach out to me via email or Mastodon if you're interested in continuing the conversation. Thanks a lot.